Yeah, we'll do it this way. So I don't know, your background, but how many of you are really chemists here from chemistry? All of you are chemical engineers, or chemistry? All of the rest chemical engineers?
Yes.
All right. So if I go too fast, you stop me, right? At any time. So I like to use the board. So when it comes to some chemistry, I like to draw a few things just on the board. Uh, I don't know the tradition of the university. I mean, we have some slides here, but I don't know, are these posted on the web somewhere for you, or?
Yeah, after lecture there.
You have a blackboard.
Excuse me?
You have a blackboard.
Oh, you do? So Dr. Abdo posted something?
Yeah.
On the blackboard? Okay, then I can ask maybe one of you to post it for me, if I email it.
We can't post, but we can share by email. I'll take.
Yeah.
Before this we are doing so.
Okay, so after each class, I will create a PDF file of this stuff, and then if one of you give me your email, then you post it for me, right?
Okay. Sure.
Because I don't know,
How
the
can
web,
problem?
the web design here, all right?
Sure.
Okay, I appreciate that. So any questions on the, after each class, I'll stay longer, as long as you have questions, I try to answer. But during the class on any subject, anytime interrupt me, especially if I'm going too fast, maybe, all right? So I don't know what you've done in the previous classes, but today we will start with something that is very essential to the refinery and the petrochemicals, right? And that is hydrogen, right? In order to make hydrogen, we use essentially two main processes in the field. It's known as catalytic reforming. Both of those are known as reforming, but one is based on steam reforming and one is based on naphtha. Naphtha reforming, which we put, it produces our gasoline to put in the cars. So we will start with that today and try to finish it, right? The process, the catalyst, the main chemistry, and then if I have time, I will go to steam reforming. But today we will start with the essential thing that is, every chemical reaction in hydrocarbons, right? We will need hydrogen, and the hydrogen has to come from somewhere. And that is the most important thing actually in the refinery. As we age in sophistication of chemistry, the hydrogen has to come from somewhere. And it typically comes from the crude oil, but from the light fractions. And if that is not enough, like the naphtha reforming, we use methane, which methane, as you know, has the most efficient hydrogen carrier, right? It has 2 moles of hydrogen equivalent. And plus, if you put the steam on it, right, and you do chemistry with the steam, now you have hydrogen that you can borrow from the steam. So it's the most effective way of making hydrogen. So, without saying further ado, now we can go and start the. Okay, as I said, there are two key reforming processes, right? One is the catalytic reforming, and the other one is the steam reforming. We will start with the catalytic reforming, which starts from a naphtha feed. As you can see, what do we call a naphtha? A naphtha is, you take your crude oil, you distill it anywhere from C6 to C11. Typically C10 is called a naphtha fraction. And you use this naphtha, which is lean in aromatics. When you convert the naphtha to aromatics, you satisfy a lot of things. First of all, you produce something that goes to the gasoline blending that you put in your car. The next thing is that you produce the cornerstone of petrochemicals, which is the aromatic ring, that is benzene, toluene, and xylene. The third thing is that you produce also hydrogen, which goes to hydroprocessing, adding hydrogen to the heavy cut, and it's all integrated. The second thing is that if this is not enough, usually for the refiner this is not enough, because the hydrogen potential in naphtha is not as high. Anywhere to 5 to 10% you will get. But if that's not enough, then you go for the methane, right? This methane molecule. Then you do reforming on it with steam, and that yield is 20 to 30%. So, but you invest more, but at the end of the day, you get your hydrogen, and then you can do methane syngas. I'm not going to go to this chemistry, but we make the syngas. After the syngas, you can create molecules, heavier molecules from the syngas. So I'm not going to go in detail in this lecture on the syngas to heavy materials, but I will go and talk to you about how you steam reform methane with the stuff that we learn on the basic catalysis that we learn in the reform. Okay? So this is the summary of what we want to accomplish today. So we will just talk about in detail reforming. If I have time, I will touch this. If not, I will move it to the next lecture. Okay? All right. Yes. Any questions so far? Okay. Can I close the door now? You think we're all in the class? So the official time for us is like 4:40, right? The class is 4:40, right?
4:45.
Oh, after 4:45, I stay and answer questions you might have from either previous lectures or whatever. Or during this time, this lecture, as I said at the beginning, some of you were not in the class, you stop me, interrupt me anytime if I go too fast, or ask questions here, right? As we go along. I think you will learn all together. All right. So, as I said, I mean, this is one of the cornerstones of refining, of how you do reforming, because it touches a lot of things. Here's like the 7 starting raw materials for everything, right? Petrochemical industry. As I said, the 7 starting materials, benzene, toluene, xylene, they have to come from somewhere, because in the natural crude oil, like the Arabian light or the Arabian heavy, your naphtha is not rich in aromatics. It is rich in hydrogen in the light cuts, but you have to reform it to go to the aromatics so we can increase the octane for gasoline. The other thing is that you usually go for methane to do the steam reforming, but this is the cornerstone also, because from methane, which is natural gas, right, we can go to a syngas, CO plus hydrogen, and you can polymerize the syngas to do liquids, like C3, C4, this is called a Fischer-Tropsch. But we're not going to go through the detail of that one in this lecture. The other thing here is that the other group that is essential is the light olefins. And what we mean olefin? Olefin is a double bond unsaturated hydrocarbon. So this will be what? What is this molecule?
That's it.
Ethylene, right? Almost, right? So we put 2 hydrogens here, right? To complete the octates. So this we call ethylene, right? Or ethene sometimes it goes. The same thing is propylene, right? And the propylene can have some isomers again. So we got 4 bonds here, 1 bond. So these molecules, propylene, ethylene, when you alkylate it with benzene, it will go to cumene and ethylbenzene. Ethylbenzene goes to styrene. So this is all tied up together, right? So when you go to the light olefins by any means, which I will discuss that next week, other lectures, by cracking or something. So in general, these molecules here, there are 7 molecules that you can start and go to the petrochemicals right away. So these are like 7 molecules almost that we can start anyway. Okay. So these are the structure of the BTX molecule. You see the benzene here, the double bond in each one which rotates. It's an olefinic rich system. That means we have an electron cloud in the pi bonding, and this we take advantage of by activating the molecule. So in other words, there's a double bond in each place which rotates. The double bonds always rotate. The toluene is next best, right? This one is in the intermediate. You use this one to go to xylenes. And the xylenes, of course, are the key for polyethylene terephthalate, all the polymers, especially the paraxylene. So you're going to make these 3 molecules, right, using the naphtha. The first thing is that you aromatize the naphtha all the way to the maximum aromatic yields. So, and these are the cornerstones of all petrochemicals. Okay, where do we use the xylenes? Suppose that I got the mixed xylenes. Where do they go? Well, most of it goes to purifying to paraxylene, and after that is terephthalic acid, and then dimethyl terephthalate, and then you polymerize, and this is the PET, right? The resins, and this is the big business. This cycle here. So the orthoxylene is less on demand, and the good news is that you can purify to orthoxylene with just simple distillation. You cannot purify the paraxylene with a simple distillation because it co-boils with ethylbenzene, right? Methazylene and paraxylene. They co-boil very close. The methylxylene has also a little bit used in PET resins with certain properties because we can change the chain length and stuff. And then only a little bit for solvents. So the xylene mostly is going for your water bottle, plastics, polyethylene, terephthalate, or anything derived. The benzene is a bigger builder. The benzene can go to cumene, ethylbenzene, and all the other stuff, all the way to nylon, all kinds of chemicals. And you know, it's really the cornerstone. And it's used in a lot of dye stuff. You know, things that you dye your clothes in. You sulfonated it, it becomes blue. You protonated it, it becomes orange. All kinds of stuff with the benzene. But today, in this class, we're going to talk about how to make cumene and ethylbenzene, right? Those are the two things we will talk in the next 2 weeks or so.
This percentage, what does this signify?
Yeah, in the past, I mean, this was in a year, and I said here they're not up to date, so this will signify how many millions of tons, right? Millions of metric tons it was produced in a year, and how much of percent of that went to this, went to that. But these are not up to date, it's just to give you an idea. Yeah, every year these statistics change. But still, I think most of it goes to styrene, you can see, right? Well, the next best is the cumene and other special chemicals that are here. All right, this is another picture, a little bit better, ethylbenzene to styrene, polystyrene, so you can follow what is happening to the aromatics, right? Essentially, it says the same thing in one picture as opposed to 3 independent slates. The toluene actually here is your intermediate. The best way to proceed is you use the toluene, right, in order to make more xylene. That's the key. Toluene is typically not an in-demand product. It's an intermediate. Benzene is ready to be sold, right? Xylenes are ready to be sold, but your toluene is typically intermediate. And the other heavy aromatics are used to make more xylene, like C9 aromatics, C10. They are used to make more xylene. But I'm just giving you this fast history here. I mean, okay, the benzene was always in 1825, but it's kind of a war thing. It was discovered in 1825 and then started to make dyes and all kinds of stuff. The toluene, same during 1937, but I think, you know, you wanted to produce in mass amounts, right? So this is the time when it went to mass production. Many applications, of course, some bad ones. Xylenes, okay, this one is more in demand. People realize that you can make some polymers out of xylene that have certain properties, but then, you know, the thing really started to kick off in 1930s with the paraxylene boom. So you can follow that. There's not much here. So the production, as I said, the key here is the reforming. So the catalytic reforming is the key to making the aromatics. Because you already have the naphtha in that range, C6 to C11. So you use the catalytic reforming process to make efficiently aromatics and hydrogen. The next best source will be the pyrolysis of gasoline. So what is pyrolysis? Anybody have an idea? The pyrolysis, yeah, ethane steam cracking, it's called pyrolysis. So you take ethane or naphtha, you steam crack it. As a byproduct, you make an aromatic stream that is called pyrolysis gasoline. Out of this aromatic stream, you can extract or separate the benzene. But this second route is not as common as the catalytic route. The most prevalent is the catalytic route. The other one is the coke oven gas oil, right, which is called also the benzol. Anybody know what a coke oven is? So you take your residual oil, right, at the vacuum residual level, at the very, very bottom. You feed it to a few cokers at high temperature, no hydrogen in the system. The thing cooks up on the surface of the drums. While cooking, you transfer hydrogen to the light material, and then it makes also an aromatic byproduct. So that's like coking, you know, coke oven technology. All right, but the most prevalent one that we're going to discuss is this guy here, catalytic reforming, because it produces us hydrogen and aromatics. All right, So there are some statistics here on, with the catalytic reforming, typically your reformate, right, we call this reformate, will have mostly tauine and xylines or CAs, right? And this is the key here. It will be mostly tauine, a little bit of benzene, not much. And that is the value of it because you want to make more xylenes, right? Then you've got the toluene to make xylenes and the heavies. You see these C9, C10 aromatics? These guys efficiently combine to make also more xylenes. Once you're in benzene, you need to methylate the benzene. And that's another technology that it's possible to methylate the benzene selectively, but you can use methanol, you can use light aromatics like ethane, propane, but we're not going to discuss that chemistry here. You know, in terms of pyrolysis gasoline, you will see that if you have a pyrolysis gasoline and you push your steam cracker at mild conditions or even severe cracking, again, you will see that the product is slated towards benzene. It's not slated towards the toluene and the xylene that you want to make. And the coke oven is the same, heavily on benzene. So that's why it's the beauty of a reforming process that if you want to do petrochemicals, especially making xylene, so the reforming process is the key to making you the aromatic rings that you need. Right? And also it makes you the hydrogen that you need for the refiner. Okay, and this is a bar chart to show you that, okay, in catalytic reforming, toluene, right, and the xylenes are the most, the precursors are the most prevalent, right? In the other sources, you always have a lot of benzene to deal with. All right, so in the catalytic reforming process, which was invented, by the way, Honeywell UOP, at the time it was UOP, right? There was a scientist there, Vladimir Ipatiev. He ran away from Russia during some revolution, right? The Bolshevik revolution, and he went to the United States and he started a small garage shop there and he was experimenting and he found out that, okay, I take the naphtha, I pass it over some catalyst with the right composition with a platinum on it, I can do effectively the dehydro. So that is the cornerstone of this project process, and today we practice it. It's running all over the world. We can discuss in detail how that works. All right, so this is how it works. This is an example of, this is a trademark. It's called continuous catalyst regeneration reforming. This is a trademark that UOP Honeywell uses. So essentially, you have to pass your feed to many reactors, and this tells you that why, because the chemistry is so demanding and complex that you need not only one, four, and the catalyst has to flow, right? And only certain part of it is circulated back to a regeneration unit, and this happens continuously, all right? So that's why it's called the continuous CCR, continuous catalyst regeneration. So the catalyst always stays at high yield, no matter what. And then you can only make up a little bit as needed during the year. Otherwise, it runs continuously. A little bit of a make-up catalyst. So now let me ask you, you know, in the audience here now, can you run this system, right? Remember, this is gravity, right? From the top to bottom, the catalyst has to circulate, right? Guess what shape is it in? What kind of shape do you expect this catalyst to be in? Yeah, good point. So if it's sphere, it has the maximum possibility of rolling like your typically billiard balls, right? So by gravity, you adjust the circulation rate. It has to be strong, right? The sphere has to be strong. And then we regenerate it on this side to remove the coke, recondition the metal, and then introduce it back. Okay? So this is a pictorial representation of what's going on, but the notion that the catalyst is sphere is, I think, one of the striking ones, because if you put extrudate cylinders, they will crash and they will not flow as well as the sphere. Okay? So, what we learn now is that in reforming, right? So the catalyst, right? First of all, it has to be mechanically strained, right? And then in order to flow, we know now that it's typically a sphere. That's the first attribute of it, right? Now the second thing is that, well, we have to find a good binder and a matrix to make this strong, right? How many of you know what is the best binder for this catalyst? What is the metal oxide support for the best one? Any ideas? Alumina, yeah, you're right. So it's the alumina. It's called alumina because it's in the oxide form, right? So how many of you know what is the property of the aluminum itself? At what charge we will have the aluminum in order to balance this? Yeah, are you a chemist? Who's the chemist? Raise your hand. Okay. All right, we got a chemist there. He's going to tell us if he's here. So, okay, so he's saying plus 3, 2 times plus 3 plus 6. We know oxygen typically is minus 6, so that's a balance. But remember, this is not a single molecule, okay? I will show you later the structure of this is much more complex. It's actually a chain that never ends. And it's not a material that is microporous, okay? Microporous is a zeolite. This material is mesoporous or macroporous, okay? All right, so now we have the kind of ingredient for the catalyst, right? So now we have to move ahead and see what other features we need in order to make the right catalyst for this process, right? So what is the next step you think that in order to make the reaction go, right? What kind of reaction we need here? We need the dehydrogenation, right? So we put here, reforming. The major thing is we need is dehydrogenation. So we have C6, say, a benzene is C6, a cyclohexane is C6 and H12, right? So we have plenty of this in the naphtha. So we have to go from here to a benzene, right? Then how much hydrogen are we making?
3.
Yeah. And then we balance the thing. But this reaction here is an example for you. What type of reaction is this? I have 1 mole on this side. I have how many moles on this side?
4.
Yeah. In thermodynamics now, who's going to tell me? I think, I could be wrong, but high pressure will favor this process. What do you think? Is that correct or wrong? Yeah. So, what kind of reaction is going to favor this guy? What pressure? Low or high?
Low.
Low. Yeah. So the pressure has to be low. Why? Is it clear to everyone? Is it clear? Yeah. Is it clear, or do I need to show you why? Everybody understands this? That the pressure has to be low?
No.
Not for you?
No.
Okay, so the equilibrium constant, right, is defined what? From the composition of these, right? The products versus the reactants, right? So let's define it now very quickly, right? Based on partial pressure, right? Or say the molar fraction. So if you divide it by the molar fraction, so we have the molar fraction of hydrogen in the product, right? Let's call it Y. It has to be to the cube, right? Because it's the third order, right? And then we have the molar partial pressure of the benzene, right? Now in the denominator we have the cyclohexane, right? So now what do you substitute? In an ideal case, we need to deal with partial pressures, right? So you need to substitute for Yx, you need to substitute the partial pressure divided by the total pressure, right? So if you substitute that, right, now you will see that in the denominator, right, we will have a term. The equilibrium constant will be proportional to 1 over, right, 1 over, and some other stuff here, which we can derive, but it's 1 over, you see, p to the third at the bottom, total, right, times this, it's p to the fourth at the bottom, and p to the 1 at the top, right? So this thing is 3, right? So that means that as I raise my pressure, actually, the equilibrium constant goes, that's the only reason. Y. Okay. All right, so this is clear? I do have some Unisim simulations to show you. How many of you use the Unisim? Unisys, Unisim, HISYS? Okay, same thing. Unisim, HISYS, you see. So, you know, I have some examples for you, but this is very important. So we know that the pressure, right? The pressure has to be low, right? So, process, right? So we write the process parameter. So the pressure total has to be what now? Low, right? That's the key. Now, it may not be apparent now, but what about the temperature? A big guess on the temperature? Does the reactor temperature has to be low or high? Well, what do you think the reaction is? Because we are making more moles now. Yeah, endothermic. So what favors an endothermic reaction? Yeah, endothermic reaction is favored by high or low? Yeah, got it. So that's the key. You see how easy it is to be a process engineer? That's it. Now we find out what process conditions we need. Now we're going to find out, almost we're done with the catalyst. Now we're going to put some features in order to satisfy the low pressure, right, and the high pressure chemistry. All right, so what kind of chemistry do we need? Now the first thing we said, we need the dehydrogenation, right? That's number one. The second chemistry we need is what? So we have a very effective way of converting a naphthene, right? A naphthene is called, this called is naphthene to aromatic, right? This reaction. Naphthene is your cyclohexane, right? And aromatic is your benzene. Now imagine, not all of our, this is easy. This is easy. But let's start with the easy. How you think I can convince the molecule to go from here to here? What do I need? What type of catalyst functionality do I need? To go from here to here. That means I need to do effective hydrogen transfer, right? Well, what type of feature do I need? Yeah. Well, I need what? You tell me. What type? So first thing is I need a metal function, right? Okay, the next question is then, can any metal, can iron do this? Iron. Okay, what can you do it? Platinum, right? Did I hear it? Platinum? Noble metal. Noble metal. And that's what the scientists from Russia figured out. Okay, essentially in 1930s, he figured out that if I put platinum here as a starter, it could be palladium, but the palladium is less active than the platinum. So the best guy, that's why we paid the big bucks for the platinum, that the best guy is this, right? We paid big bucks. Almost as more expensive than gold sometimes in many situations, right? All right. So we need the metal function. The platinum, well, what is it going to do? It's going to be an effective hydrogenation catalyst and a dehydrogenation catalyst, depending on where you run it. If you run it at low pressure, right, as we wanted to run it, right, it will be an effective dehydrogenation catalyst, right? Platinum will make the hydrogen. We will soak the hydrogen in the hydride, make the hydrogen. All right. So the second though things that we need, well, okay, the platinum will do this reaction for us. What else do we need? We don't only have everything in naphthenes, right? We do have also paraffins that we have to deal with, right? And one example of the paraffin is what? Normal hexane, right? What is a normal hexane? Well, it's a long molecule, right? It's all saturated, 4, 6, right? In each end, I have to have hydrogens here, right? Now the question is, what do I need to get this guy to go to the benzene that I need? Well, I need cyclization first, right? I need to cyclize this thing. Also, what is called is dehydrocyclization. So it's not enough to do cyclization, you have to do dehydrocyclization. And how do we do that? Yeah, that's the next thing. What functionality do I need For dehydrogenation, I have the metal, right? I have that in my case. Now I need to activate this paraffin. You can activate with the help of a metal first, but you need the acidic portion. The acidic portion. So acidic or acidity. I need the acidity, right? And that we write it here. So the first, now we need the acid function. Okay. Now remember, what type of acid function, right? We start with the alumina, right? So is the alumina acidic? Let me ask you this.
Yes.
Yeah, to a certain degree, right? It's acidic. Okay. So now we know that the support can act in the right form with the gamma alumina, right? This is gamma alumina. It will act as an acidic component. Okay? All right, so far all good? So we list now. We need the sphere. So we need a strong support for the metal, which is the aluminum oxide. It has to be in a certain form, like the gamma alumina. All right? And then we need the noble metal. We can have promoters in the noble metal, but the noble metal alone starts the thing, right? The modern catalysts are not satisfied with only platinum. They put promoters, all kinds of other stuff to tame the platinum to make sure that it doesn't crack or it doesn't do hydrogenolysis. But essentially, this is the reforming catalyst. Okay? Any questions on this so far? Okay, all good? Understood? All right. You have a question?
Yes.
Yeah.
If the acid contains beta function and acidic function, won't the acid function be affecting desired, like the first one that requires beta function?
Okay. The question is that if I have acid function, right? That's why we do this simple at the beginning. You see, we use little catalyst, increase the space-time. So all this stuff, all the simple stuff, happens at a very short residence time. So that once it's aromatic, the acid cannot touch it. It's so stable. You see that? Do you see that from the picture? The first bed of catalyst has very short residence time. Why? Because it's very little, right? It's reactive. As I go down now, I need to do this tougher reaction, so I put more catalyst. This is how you adjust it. You're clear? Or? Good? Or?
Why in some cases they add fluorine toxic?
Yeah, that's another one. See, the acidity of the alumina alone is not enough. You increase, enhance the acidity by adding chloride, which brings to, for those of you who are chemists, which brings me to the real course, part of the course that I like. If you're interested only though, if you're not interested, I won't go into details. So how many are interested in to see the chemistry of the alumina, where the chloride goes? You're interested? Okay, then I go and do it. Because if you're not interested, then I won't do it. Because I don't want to waste your time. Okay, so this board is here. Can I write here?
Sure.
Can I write? Okay. All right. Okay, can you see it from there to here? Yeah. All right. So the first thing I need to do is then define you what the aluminum is, right? So okay. Maybe I should. Can I erase this?
Yeah.
Yeah, because there are some things that I don't want to write in slides for many reasons. So how many of you are pursuing a graduate study in the chemical engineering for a master's degree or a doctorate? All of you, almost? Okay. So probably by now, how many of you selected a project to go on and do a project? How many of you has a master's project or a research project?
In catalysis?
Anything. You decided? Did you decide already?
Yeah.
Okay. So maybe, I hope some of this might help you to pick one for the right supervisor. Yeah, so, okay. Well, where does the acidity of the alumina come from, right? And typically, the alumina, it's perfectly bonding, right? And it's a chain. right? You have to have 3 bonds on the alumina to satisfy the +3 condition, right? But if it's a zeolite, then it's a different story, which we'll touch that later, right? So once you have the hydroxyl, so it's a little bit hydrated, right? Now you can see that the bridge continues, and you make another hydroxyl, and voila, it continues all the way. Again, oxide, aluminum oxide, aluminum oxide. So this guy here provides you with the protonic acidity. Okay? Now, this acidity here, and this being the minus charge, because this is sharing, each bond is a 2 electron, right? So the question was, okay, why do we put chloride on this stuff? Well, the short answer to that is that if you put the chloride on it, right, now we have a situation where we can add the chloride in terms of an acid, hydrochloric acid. Typically what is done is that during the manufacturing, during the process, right, we also sustain a certain amount of chloride on the catalyst, right? So now once you put the chloride on it, typically what it happens is that in this bond, now you're going to take the minus, right? The minus portion of this. So suppose that I want to add the chloride. So now the chloride will attack this guy because the net charge here is -1, right? This guy is also -1, and it will exchange itself, right? You understand this, right? The minute this becomes now the new chloride in alumina, it will change the acidity forever on the neighbor. That's the theory. So the property of this net charge now, right, is impacted because now this guy is full of electrons. So we made it more electronegative. So this, by replacing the right amount of chloride, you increase the acidity. Now, because this is a tunable thing, typically about 1 to 2% chloride you can you install on a gamma alumina theoretically, right? So you try to be in somewhere, if you put too much chloride, then you see cracking, a lot of bad reactions. But if you don't put any chloride, then you see that the hydrocyclization reactors have to be bigger, much bigger at the end, more than, but if you put the right amount, about 1%, right, then everything has its own balance, so there's no selectivity issue. And the dehydrocyclization reactions, all those proceed, especially at the last big reactor. This is where we do most of the tough conversion of the paraffins to aromatic. Okay? Any questions so far on this? Now the question again, right? Where is the acidity of the alumina come from? So we know the concept of Bronsted and Lewis acidity, right? Is that correct? So who's going to tell me now, when I have this alumina, right? We discussed that it's already +3, right? Then we got the chloride making bonding on it. How many chlorides I can put in an alumina? Yeah. So, but each one, though, we have to be careful. Each one is a covalent bond, right? So now you satisfy the octet rules. 2, 4, 6. You have 2 vacant, and that's the key. That means this is in the Lewis acidity, the alumina, Lewis sense, that another definition of the acidity is it's an electron pair acceptor. This is the Lewis sense. Why it's acceptor? Because it's missing the 4th vacant 2 pairs of electrons. So if I have a basic molecule like nitrogen and it's dangling around, right, with all this might, right, it's dangling around, these electrons we want to associate with this empty site. And that's what the acidity comes from. All right, so for those of you who are going to pursue some graduate level work, right, in the aluminas, the most important one to characterize how effective is the acidity on an aluminum, to the best of my knowledge, is what I call the hydroxyl IR. So in this region, once you hydrolyze the alumina, then you put the beam of near infrared, and you get the spectroscopy. The way where the shift occurs, you will understand for that alumina what type of acid size do I expect. Okay? Almost spend the. All right, are you interested in that? All right, let's go with the hydroxyl ion then. What type of sites? So I will draw you one example, right? The most common site is that what we call the tetrahedral coordinated alumina, as we have here. You have one hydroxyl, right, giving you the acidity, but then you have three neighboring bonds. Each bond can be an oxygen, typically, and then a silica or alumina, right? This continues, right, like this. Oxygen, alumina, oxygen, again alumina, oxygen, right? It continues forever. So the infrared will tell you that if you have a peak at this shift, which is by wavelength, right? About this one happens to be about 370-50 to about 307-80. You will notice a strong peak in the spectra, right? And the peak will be very strong, and you read the wave number, right? It will correspond to this. So when you see this peak, this means that you most likely have alumina coordinated this way, all right? And what happened here? So the net charge here is +3 divided by 4, right? Because the aluminum has +3, right? Is that correct? Is this correct? So we have a net positive charge. But there are 4 bonds that has to divide this positive charge, right? Now, on the other hand, we have only, for this case, right, we have only one negative one, which is -1, right? And that sits right here. The charge here, remember, is -1. But one bond will -1. So the net thing is minus what? -0.25, right? So this is the net charge that we expect on this. So I want to say that this is a way of looking at it. If the charge is negative, what does it tell you? Well, if the charge is negative, this structure is not that acidic. It is, but it's mildly acidic. The positive, the better. The greater than 0, the better. Okay? Now, what's an example for that? An example for that will be, say, the most acidic one that you can encounter is an alumina that has the neighbor, right? The neighboring alumina. Again, we have the hydroxyl group here, right? On this alumina. It's talking to another alumina, right? Next to it. So this hydroxyl is bridging 2 alumina. On top of that, it's bridging the 3rd alumina. Now, each of those guys, right? Each of those guys can be not tetrahedral coordinated, but octahedral. Octahedral coordination will mean that we have 3 bonds on each. 6, right? Total 6. So here we got 2 bonds here, 2 bonds sticking here, total 6. Another bond here, 2, right? So now if we do the charge counting, right? What do you see here? That's the key. First of all, how many aluminas do I see? I see 3, right? Let's write 3. I have 3 aluminas. Each one is a positively charged +3, right? Each bond now, positive charge, is divided by 6, right? That's now how many positive charge do I have for this, right? Now I need to count how many negative charges I have, right? And what is the answer for that? How many negative charges are there? What? Are you going to help me, or we're done? Okay, -1, right? We still have this guy -1, right? So now when we do the math here, you will see that this will be plus 0.5. So this is more acidic than this. Okay. And the way you characterize these are, and there are like 4 or 5s, you can open a book, I think, it's called the hydroxyl IR spectra. But if you're interested, then I can make, I can, next lecture, I can write it over there and you guys can copy it. But there are essentially 5 types of alumina that you will detect in the hydroxyl IR. I wrote you the 2 of them. The most acidic one is this one. Okay. So the next thing is that, how about Lewis acidity? Where is the Lewis? Because we learned that, okay, aluminum chloride is acidic in the Lewis sense, but how does it translate to the aluminum oxide, right? So if you look at that, we have the alumina here, right? And we have the hydroxyl group on the surface, and this alumina has to talk to another oxygen, right? And so forth. So you still have this hydroxyl here, right? So now each of these aluminas can be 6 coordinated, right? 3, 6, you see? Another one here, maybe 6. So now when you heat this up, remember heat, right? That means you're going to remove some of the water, right? As you heat it up, right, you're going to move now some of the water. At that point, we get the Lewis side, we get the Bronsted side, okay? So remember now, we have to remove the water, so the most likelihood candidate is this guy and this guy. They want to travel away as water, right? That's one of the logical things. Or we can do the reverse. We can take this guy and borrow the hydrogen, and then it will go away as water. Either way. If you take this guy, then we can continue and say, okay, now the molecule doesn't have this bond, right? Instead now, it's positively charged, right? Still, we got this, so this will be your Lewis side. This is the Lewis. So and then still we continue, right? We have a negative charge here, because we only move the hydrogen, and this will be the basic side. You can further move the water, right? You can get more water out, or hydrolyze it. Once you hydrolyze it, then we get this side becomes the Bronsted side, this side is still the basic side. So, same thing. But this is the difference between the Lewis side and the Bronsted side. So in reforming, if you have Bronsted sites, it's not good. Typically, Bronsted sites are associated with zeolites, and it will crack the heck out of your feed. The Lewis side is the most important. So that's why in order to prevent forming a Bronsted site like this, we put chloride on the tail. Okay? Any other questions? So we discussed how this thing is, chloride is modifying the surface, but then we have to put the metal too, right? So the metal is typically in the form of chlorine. So there is another coordination with the metal. So the platinum, typically we will replace the H plus at the end of the day. So the platinum will be associated all platinum, and then you reduce it, and it will be just platinum metal. But okay, So at the end of the day, we got the platinum on gamma alumina, right? And we are chloriding it. Now, in recent years, in order to satisfy the operation, right, over the years, they made improvements to the catalyst. I mean, this catalyst that we discussed was invented in 1940. So since then, they are changing the alumina support. They are making it more robust, more surface area, right? Everybody knows what a surface area is. So the surface area on an aluminum oxide, surface area is how much a meter square surface area I have per gram. So the higher I have this number, the more metal I can add to it. Because I need the surface to impregnate, right? If I have little surface, I won't be able to impregnate anything. So that's where the type of alumina is important. So if you start with an alumina in boehmite form, and you heat treat it at 600 C, typically you go to the gamma alumina. In this gamma alumina phase, you have the highest surface area, 200 to 300 meters square per gram, typically. As you heat it up to 900, now we are sintering the alumina, right? We are removing, heating means removing the hydroxyls, right? We are collapsing it, right? Like it's over there. As you collapse it, now this is what we call theta alumina. In the surface area range, this guy is anywhere from maybe 20 to maybe 80. You further heat this thing to 1200 C. Now you're in a phase we call alpha alumina. Okay, so far you're with me? As I heat it up at this temperature, 1200 C, now the surface area can be less than 5. I lose all the surface area. But what happens to the crystal side, do you think? So the crystallines are mostly small at the gamma alumina phase, right? So crystal are the crystals of alumina, right, together. So you can see the small crystals I have more surface area, right? Don't you agree?
Yes.
Right, they are segregated. When I collapse it, now some of them try to sinter together, right? And by the time I'm here, and when you sinter together, now the surface area is low. Yeah. By the time I'm here, right, I have these huge large crystals, only one or two that probably occupy the entire sphere. Sometimes they collapse. So the only surface area you have is this small surface here, right? So that's why now the alumina collapsed, and the surface area is very low. You can still use it as a catalyst, but not for reforming, right? Because we need activity, we need the metal, so you can still use this, but not for reforming. Maybe hydrogenation to minimize, side reactions. Like we can do the reverse with this. Like take a benzene and go to cyclohexane, right? To minimize the side reaction. But this is the story of the alumina. So over the years, the inventions since 1940s were situated on how to best make the alumina. First of all, stable, high surface area, right? They have to be stable so that they don't collapse the surface area like this when you heat them up. And the next thing is how to improve the metal function. I'm starting with platinum. Everybody knows the platinum. So the next best thing is, what do I do to platinum to prevent side reactions? Because platinum alone is too active, right? You need to do what in order to suppress its activity? Any idea? Yeah, well, you have to reduce the platinum in order to be catalytic active. There's no other way. Every metal has to be in the reduced state. And because you're in a hydrogen environment, the assumption is you reduced already the platinum. That's one thing. But what else? Yeah, the next best thing is alloy. Because if you do alloy with the platinum, then you will force it to have a different electron structure, and its activity to bad reactions like hydrogenolysis, like methane making or something, will suppress. And therefore, you can take that alloy platinum to much higher temperatures. So typical alloys that have been used since 1940, typically platinum rhenium is the next best generation of inventions, platinum rhenium, platinum germanium, and the most important one that you should know is the platinum tin. Okay? Any questions on that so far? So I described to you a little bit on the themes that also you can try in your graduate work. Because this is open research area. I mean, the people who do this come up with inventions, they improve the product. The benefit is that we have a better system out there running, less utilities, everybody wins, less pollution to the environment, but it's still open art. And maybe alumina alone is cheap, but hey, maybe the next best thing is the new aluminum, the metal oxide support that will change this forever. So it's all open for research, really. Yeah, I mean, okay. Platinum rhenium is one thing, right? We said germanium can do this. Tin is the most important one. So when the technology started with the platinum only, remember, right? They were using fixed bed because the engineering then were not so sophisticated, right? And my company, Honeywell, was selling these, right? Fixed bed. Still the tradition the same. Small reactor up front, bigger as you go along, but fixed bed. Why? Because the platinum alone, right? The platinum alone was not stable. It was making all kind of side reactions. So what they had to do is stop one of these reactors, typically the third one, after say 5 days on stream, regenerate this, and then bring it on stream again. And this one we call the semi-regen flow scheme, where I'm burning all this hydrocarbon, right? It's absorbed on the catalyst, bad for the environment, bad for everything, but they have to interrupt with the process. Once they start messing around with the platinum tin, right, all this complex chemistry changed. Platinum tin, platinum rhenium, because now the platinum is tamed, it's not doing these side reactions, which is dehydrogenation of things twice. You see, it's another thing to do this once. If the platinum is too active, it will go in even imagine we start from a paraffin, right? First, our dehydrogenation will give you an olefin. But if you do it again, it's a diolefin. And when it's a diolefin, forget it. It's unstable. It will polymerize right away. Right? And that's what they were struggling with. Once you alloy the platinum, that is gone. Right? That was the next best invention for this. And I'm giving you this, but I want to get to this semi-region thing. We can go back to this. And you can follow this chemistry straightforward. Okay. So here's a bit brief history, but I want to show you the process. Okay, the catalyst was deactivating by polymerization, right? Because of this too much activity of the platinum, you will go to the diolefin and then polymerize the system. And so the semi-regen reforming started to kind of do it where you shut down one reactor right here, right? We shut down these 3 in series reactors. We have to regenerate it, all kind of a mess, right? It has to run at high pressure because otherwise it's dying in hours. So thermodynamically, you're against it because you have to keep it at high pressure, right? We discussed it. The most favorable condition is low pressure. But at low pressure, you deactivate the hell out of the process. So then they were thinking, what the hell are we going to do about this, right? We're stuck now. We are polluting the environment. We are burning CO2 out of the wazoo. Then the next thing came this one, continuous, right? So you take only a portion of the spherical catalyst, right? You send it back. You burn in the recycle region where you regenerate it, right? While regeneration, though, what happens? So here's the key. This is a hydrogen environment, right? Right there. You see that? In this environment, the reactor is under hydrogen, right? I have to take this catalyst now from the hydrogen environment, merge it with nitrogen, and move it to the oxygen environment. Otherwise, it's going to blow the heck out of the plant, right? So first, I transfer it to the nitrogen, oxygen, I burn the coke. Once I burn the coke, my metals are all over the place. They're in oxide form. Now I need to rechlorinate the catalyst, right? Because I lost all the chloride during the burning process. So at this point, I oxychlorinate. I redistribute the platinum because platinum loves to be associated with the chloride. It will fall off. It will be dispersed, right? And then it was coming back. With this now, they can run it 50 pounds. The best reformers to this day, and I think they run as low as 50 pounds. And we make boatloads of hydrogen for the entire world. And we have many of these units, including a lot in Saudi Arabia, but around the world. So this is what we call the continuous CCR reforming. Okay? So with this now, I think I covered most of the gist of the chemistry here. But the catalyst development still continues. I mean, you first introduced this in 1980, but still people are working on it, right? How can I make the alona better, more stable? We're still working on it. So it's an open area. Research is always open, right? As long as you know the fundamentals, you can always contribute. Okay. All right, let me stop here. I think, how much time do we have? You guys told me 10 minutes, right? Yeah, okay. So, unless you have questions now, do we have any questions so far of what I explained to you in reforming? All right, so in the next 10 minutes, then what we can do is, there are some key things right here. Why is it advantageous, right? We discussed that the highest possible yields because we burn part of the catalyst. We always keep it at high conversion and high yield. We never have to take the reactor off stream. Once we take one of the 3 reactors off stream, we lose conversion, we lose yields. So this continuous system changed that all. We are getting both high hydrogen and C5 plus yields. We make the aromatics that we need. Remember, 94 is your regular gasoline, right? Octane. As you make more aromatics, we can go up to 94. The next level is 96 in the US. We sell that in 98. You sell in Saudi Arabia, I think, 98 for high performance cars. 98 is the highest rate. After that is petrochemicals. We can go as high as 106 octane. That means that all the C5 plus yield is mostly aromatics, 85%. And that's where you have to do for the petrochemicals because you want aromatics. So you jack up the severity. So it's very, flexible. If you're in the gasoline mode, you run it at low octane, it will sustain you forever. 94, 96, 98. If you need petrochemicals, you gotta jack up that octane to 106, 108, 85% aromatics, your petrochemical complex runs on. Okay. And a little bit of chemistry, right? Here, maybe I'll stop here. Okay, so the next best thing is I was thinking maybe I can show this with your flex class, but I think now that we're flying here. Oh. Now this is the second part of the lecture where we did the catalytic reforming, right? But the next reforming technology is still now the steam reforming. Right? So in the steam reforming, remember, it's still a reforming reaction. We all agree, right? So let's write the equations for the steam reforming. We can keep the alumina here, maybe. So the hydroxyl IR is something that you use to characterize the alone. Now, in steam reforming, we start from methane, right? Same thing, but we want to go where? What do we want to make?
Hydrogen.
Yeah, so hydrogen is on this side, right? Now, in order to do this, right, theoretically, we will still have more moles in the product than, so okay, what favors this steam reforming reaction? In pressure, high or low?
Low.
Low. What favors the temperature?
High.
Alright, same idea, right? You see the connection there? Now, the only difference here is now, you have the steam into the picture.
Just, I have one
Yes.
question. I have worked in a plant when we were doing this at the 30 bar pressure. Would that
Yeah.
be considered low?
30 bar for this?
Yeah.
Yeah. Oh. But the other reforming reaction is 50 pounds. So 50 pounds is 3 bar G.
Oh.
So you're about 10 times more. There may be reasons for that, right? First of all, your steam reforming catalyst, the nickel catalyst, maybe it's not stable. The management says, I don't care. I'm not going to replace this catalyst. So let me run at high pressure enough, right? Just to maintain the cycle of the catalyst. That's the main reason, I say. Because if you reduce the pressure, if you don't have a good catalyst, it's going to die on. That's my hunch. But thermodynamically, this always holds. You gotta run these things. And you know, when I say pressures, I mean, I'm not talking about like, I think 10 bar G, probably. 10 bar at the reactor. You know, for this technology, what I will suggest you to do is, if you want to learn more, this book, right, shows you where we are discussing things, right? Okay, so far we covered the reformer, right? Hydrogen, gasoline. So for the hydrogen, which is needed everywhere, right? There you go. So for the hydrogen, which is needed everywhere, the steam reforming is needed because your reforming percentages yields, right? It's only 5%, I told you, right? But the steam reforming can be as high as 30. But the only way you sustain these is to make sure that you run at thermodynamically favored conditions. If you are not running at thermodynamically favored conditions, you're either trading yield or stability. It's one or the other way around. And I don't know, you know, typically the nickel catalyst is not regenerable in this environment. Once you lose it, you lose it. You have to replace it. Okay, again, here's the chemistry, right? We have to put the water in it. Now we can make 3 moles of hydrogen. We make 1 mole of CO. But further, we can use the water-gas shift, right? You see how it becomes effective. What is the water-gas shift? I can get the CO, add more water to it, then what do I do? Well, what do I make? Yeah, CO2, but then I gain another hydrogen. So all of this adds up, okay? This is all happening in the steam reform. So steam is a way to balance. But if you put too much steam, it helps your stability, but then it might dilute your activity, so you have to trade off how much steam you have in the system, right? So steam helps your stability. But, okay, high temperature and low pressure is the favorable region. But you can see that typical, right? It has to be around 20 bar G around. So your 30 could be a little bit on the high side. And there could be reasons for that. You know, there could be technical reasons to manage the plant so that you don't spend too much money on the catalyst. It's a technology thing. Do you know who is the licensor for it?
No, I don't remember.
Yes.
It was 12 or 13 years ago.
Okay, so maybe by now they replaced that catalyst, so forget it.
That's bad.
Yeah, most likely. Because otherwise it doesn't make sense. All right. So typically, right, I have 3 minutes here. Typically the metal function, you still need the metal, but it's nickel this time. Okay, why is it nickel? Because it's cheap. You can't afford a platinum, you don't afford it to sinter, plus you're making things that are only hydrogen here. You need a lot of work to purify the hydrogen, so you want to reduce your investment. So typically it's nickel. The problem with nickel is that it's reduced in the reactor. When you have sulfur in the feed, once you make nickel sulfide, there's no coming back. You have to take that catalyst out, burn it, right? Get rid of the SOX, and that is a mess. You have to take it out, send it somewhere, burn it. So typically people don't even bother. They just replace. Okay, the best reference for this, if you want to read more, is this Mayer's book. Okay? Mayer's book on Handbook of Petroleum and Refining Processes. This is the 3rd edition. What I described to you is more involved there, more reading, more references in there. But this is just, this is a level of graduate class. I want you to introduce the concept. So these two processes that we discussed today are the main processes that we use to make hydrogen that we use in the refinery. Whether we use it somewhere else, the reforming makes aromatics and the hydrogen. The steam reforming targets mainly hydrogen and methanol. Because if you're at 3 hydrogen, you adjust this to 2 hydrogen, then you make methanol, direct synthesis. So many opportunities. You adjust this to 1 syngas. This is what we call syngas. It's called the synthetic gas. Hydrogen plus CO. You go towards 1, you use Fischer-Tropsch, you polymerize, you make olefins. You can make olefins from the syngas, right? So it's all tied up. But the main function of this guy is to make hydrogen for you. So if you need a lot of hydrogen, this is the methane. Steam reforming is one of the most efficient processes. Okay, so I get more chemistry on it. This is where you shift. And this carbon is killing you. This carbon is all on the nickel. If you run at low pressure, your carbon forms. But if you don't run at enough pressure, then you lose yield because you're against thermodynamics. So there is a balance. Okay, this is a simplified process scheme. Why is this important? Because we have, typically you have furnaces here, right? You sustain the endothermic heat, right? You gotta burn a lot of fuel here. That's why sometimes it's called also partial oxidation, because you use some of the methane to burn as fuel, and some of the methane you use to make the syngas, right? Partial oxidation also. But the most important one here is that how you purify the hydrogen. You use the pressure swing absorption, which is a technology that Honeywell UOP sells, right? So this is a set of adsorbents that are selective for all the impurities, CO, methane. They let the hydrogen go, and you can get to 99.9 purity. And the price of this hydrogen is much more valuable today than, say, propylene. It's about $1,500 per metric ton, even in the distressed market. So hydrogen is very valuable, and a refinery without hydrogen cannot survive. You need to do so many things. Okay, another flow scheme here, where instead of PSA, you can do cheap hydrogen. You can sell cheap hydrogen, but then you're not getting the premium, right? But you still have to methanate, because there is still some CO in it. You still have to do a lot of work to methanate, right? So you use some of the hydrogen because you don't want CO. CO is a killer. It will kill your platinum, it will kill anything, right? Okay. So there are some, steam to carbon ratio, but in this book, you will find a lot of information how to optimize the process. Same idea though. Here's the partial oxidation, right? It's almost the same. You use some of the methane to get the heat that you need, endothermic reaction, right? You gotta generate the heat. All right. So that ties up our methane conversion, which we'll touch next time. So at this point, let me stop the lecture and answer your questions.